Welcome again. In this talk, we go under the hood of the heating sector. How big it is, why it dominates energy, climate maths, and what conventional technologies currently satisfy that demand. This is the baseline session of this course section. In presentation 2, we will explore decarbonization pathways, and in presentation 3, zooms in on the social aspect of decarbonization. Let's start with scale. How much energy does the world actually spend on heat? According to the IEA, heat accounts for 50% of global final energy use and 38% of energy-related CO2 in 2023. That means every second unit of energy humanity consumes it is just about moving thermal kilowatt hours from somewhere to somewhere else. Scientists estimate we can emit only about 280 gigatons of CO2 from 2023 onward, for a 2/3 chance of keeping warming below 1.5 degrees Celsius. At today's pace, the heating sector alone emits 14 gigatons of CO2 every year. This means that over the 60 years of 2023 to 2028, that adds up to 84 gigatons of CO2, almost 1/3 of the entire budget. Over almost 1/3 of the entire budget. If we fail to decarbonize heat, we miss our climate goals. Now, where does that enormous heat demand actually come from? Buildings and industry are two totally different stories. Even though both demands cover a similar percentage of the global final energy, the amount of heat consumed in buildings is huge and dominant of low temperature. On the other hand, industry covers a wider temperature spectrum up to 1700 degrees Celsius. The physics of each temperature bracket dictates which conventional technology is used. If we're not talking about a district heating system, then on-site combustion occur in the building sector, while large-scale technologies such as cogeneration and steam boilers occur for the industry. Next, what fuels feed this thermal appetite? Fossil fuels still supply 2/3 of building heating energy, mainly natural gas. Natural gas alone covers 42% of building heat demand worldwide. This is 60% in the US, around 40% in the EU, and around 20% in China. China, direct coal use in buildings is still around 18%. Coal is also above 80% of fuel in North Asian district heat networks. Across global industry, over 90% of high temperature heat comes from coal, gas, oil, or coke. IEA industry tracking, modern renewables, biomass, geothermal, solar thermal, electrified heat are only 30% of total heat consumption. Having mapped fuels, let's drill into the hardware that converts them into useful heat, starting with buildings. This table shows the main ways homes stay warm today. Starting with the gas boiler family. From the one hand, we have the non-condensing, an old standard that wastes flue heat, so it tops out around 80% seasonal efficiency. On the other hand, the condensing has the same fuel but captures that water vapor heat, nudging efficiency into the mid-90s. The condensing options save 10 to 15% gas and emits a bit less CO2, but both still burn fossil gas, so they buy us time, not the final answer. Moving on to oil boilers, they live mostly in off-grid rural areas, while coal stoves linger in parts of Eastern Europe and rural Asia. Both carry the highest carbon and air pollution footprint in the table, and this is why oftentimes policies first target transition from coal and oil. Moving to non-combustion options, electric resistant heaters have a near perfect on-site efficiency, but their climate impact is directly linked to the grid mix. If there's a coal-heavy grid, then it can be worse than a gas boiler. If a renewable energy source rich grid exists, they instantly become net zero. Usually, electric heaters team up with storage options, but this is for a later stage of the courses. Modern biomass stoves, boilers, burn pellets or chips, they have a good efficiency while this option is considered as green when the fuel, so when the pellets or the chips, are certified as sustainable. And finally, solar thermal collectors. They use the sun to preheat water, however, output drops when there is no sun, for example, the winter time. So it needs to be used in parallel with one of the above mentioned options. The decarbonization toolbox will be presented in the next session. Space heating is half the building story. Water heating follows similar but not identical patterns. Typical household allocates 12% of total energy to hot water, up to 25% in warm climates where space heat is minimal. Thus, domestic hot water is an often overlooked decarb level. In terms of technologies, similar solution seems to exist for the domestic hot water needs. Now shifting from homes to factories. Industrial process heat makes residential heat at the high temperature end seem insignificant. This slide splits industrial heat into four temperature bands, each with typical equipment and fuels. Think of it as a ladder. The higher the temperature, the fewer the decarbonization options. And as we will see, the bigger the carbon footprint. On the first line, we have food factories, paper mills, and breweries that just need hot water or low pressure steam. They burn mostly natural gas and in some regions biomass chips, and they already sit around 70 to 85% efficiency. Because the temperatures are gentle, we can decarbonize these lines with high temperature heat pumps or electric boilers quite easily. So the carbon urgency here is moderate. Going to the second line, chemical plants, textile dyeing, pharmaceutical dryers, they still rely on gas and fuel oil, but the higher pressure starts squeezing out heat pump options. This band is bigger, roughly 1/6 of all industrial heat, but still manageable with today's electrification technology if the policy incentives line up. Now the third line, fired kilns for ceramics, glass, for health, steam crackers. Efficiency tumbles into the mid-60s because red-hot refractory walls radiate heat like a stove element. Electrification is technically possible, but capital heavy, so most plants stick with fossil gas or LPG. Notice the pattern. Higher temperature, steeper losses. Finally, the last line, blast furnace iron at 1600 degrees, cement clicker at 1450, glass melts at 1400. In energy terms, this slice is only about 1/5 of industrial heat demand. But here's the kick. Because these furnaces burn almost pure carbon fuels like coke, that's coal baked into a hard high carbon sponge, and because cement literally releases CO2 from limestone, this narrow slice punches far above its weight. Add steel, cement, glass, and a few non-ferrous metals together, and you get roughly 15% of all global CO2 emissions, 3 times their share of heat. So a small energy slice becomes a giant carbon slice. So three parting comparisons to log in. Temperature narrows technology choice. Carbon intensity climbs the hotter you get, roughly quadrupling from low temperature steams to a coke-fired blast furnace. Decarbonizing that ultra-high temperature top rank is the single biggest lever in industrial climate strategy, even though it looks small in an energy pie chart. Most homes are heated one by one. but in about a tenth of the world's buildings, the warmth arrives through a giant central radiator called district heat. Think of it as a city-scale kettle that sends hot water or sometimes steam through an underground loop and lets every building tap in through a heat exchanger. How it works? The source is one big boiler house or a combined heat and power plant. Pipes are heavily insulated supply and return mains like the arteries of the system. Buildings take the heat they need, then the cooler water heads back for reheating. District networks cover about 9% of building heat worldwide, but the map is patchy. Fuel mix today is still heavily fossil. In China and much of Western Europe, more than 80% of the heat in these pipes come from coal-fired CHP. In Western Europe, it's a blend of gas, biomass, waste to energy, and a splash of large heat pumps. So what are the benefits of district heating? Economy of scale. One big efficient plant is simpler to clean up than 10,000 little boilers. Second, flexibility. Swap the fuel at the plant and everyone downstream decarbonizes overnight. No plumbers in people's kitchens. However, they have some heat losses. Even well-insulated pipes concede 5 to 25% of the energy before it reaches customers. So, picture district heat as a giant vessel. If we cool the water down, patch the leaks, and change what's burning in the plant, we can turn that vessel into a clean heat backbone. That's exactly the make of story we will tell in some later presentations. Now, heat is half of humanity's energy diet and close to 40% of our CO2. Ignore it and we miss every climate target. Most of that heat still comes from combustion technologies that can get much cleaner. The efficiency ceiling is already in sight. The hottest 10-20% of industrial heat is the carbon heavyweight. Small slice of energy, giant slice of emissions. Why does that matter? Those facts tell us where to aim our effort. Electrify the low temperature masses quickly and throw the innovation kitchen sink at steel, cement and glass. In the next session, we will crack open the decarbonization toolbox, heat pumps, electric boilers, green hydrogen, bioheat, efficiency retrofits, smart controls. So we will see in the next presentation how we can decarbonize the heating sector and what are the upcoming technologies.